Alright, this is Lab 5, and I decided to do the falling slinky problem. So, introduction. What is the problem? We're going to analyze a video of a slinky falling, and we're going to do that with both a real-world example, which is the sample video, and a computational model that I'm going to create to see if the bottom of both of the slinkies stays stationary as seen in the video used for the real-world example. So why are we interested in this answer? It's going to help us better understand the motion of a falling object and how to track the center of mass of that object and whether or not that's accurate in both computational models and real-world examples. So a quick summary of our results. This lab house shows how when following the center of mass of a slinky, the entire system is not necessarily taken into account, aka the extended system, which causes issues between the computational model and the real-world example. So now we're going to talk about our fundamental principles. First, we have Newton's second law, which is delta p over delta t, or change in momentum over change in time. And from Newton's second law, we're going to use the velocity update formula, which is final velocity equals initial velocity plus the net force divided by the mass times the change in time, and the position update formula, which is the final position equals the initial position plus the average velocity times the change in time. So our net force is going to be the drag force due to air resistance, plus the force of gravity, plus the force of the slinky. Now the force of gravity is going to be mass times 9.8, which is just the acceleration of gravity. It's going to be negative because it's pointing downwards. The drag force is the absolute value of the velocity squared times v hat. It's going to be positive because it points upwards. And the force of the slinky is the tension in the slinky. You can see it's kind of unwound like a rope, which again is going to be positive. So we're going to go ahead and show you the video I used on Tracker. So here we are. He's just dropping that slinky. You can see the center of mass is the one that's being tracked and it drops all the way down. This will also kind of show you some of the potential issues that we found because there are a lot of troubles with the frame rate on this video when downloading. And you can see the graphs that it's made over here, which I'm going to show you again in just a moment. And so here is the graph of x versus t. We're not really worried about this because it's meant to be a very small discrepancy. That's just issues in how we tracked in the frame rate. But what we really want to look at is the y versus t. And so it follows this sort of downward trend. Obviously, there's a few bumps, again, most likely due to the frame rate. And here is the data that we collected. You can see the time starts right at 0, but it doesn't actually start falling until about 0.3. So when we do our coding, we're going to set it at about 0.3 just because that is when it actually starts to fall, as you can see in the rapid change in y values. And the time ends at 0.667, which again, you're going to see in the code. So here is our code for today. We have everything set up with the ball, the plot. The mass right here is 0.25 because that's the mass that we're predicting our slinky is going to be. We have our magnitude of acceleration due to gravity is 9.8. Our proportionality constant for the drag force. And then we have while time is less than 0.3 because that's when we're going to start falling. And we have everything set out with the net force, the velocity update formula, the position update formula, and advancing the clock. And over here, you can see we also have between the total time, 0.3 and 0.667, we again have our work, our forces, our net force, our velocity update formula, our position update formula, and advancing the clock. And I'm going to go ahead and run that for you so you can see how we got this graph. So we're going to run this program. And you can see how this position versus time graph was then created. Going back to our slideshow. So here's our position versus time graph that we made, and it's going to go all the way to 0.6 on the time scale, and it goes down to -40 over here. And so again, we're going to look back at this original graph that we had. So let's look at some of these discrepancies. So we do have up to 0.6 on the time scale, and I think one of our main issues here was that it goes down to -0.4 instead of -1. This has a lot to do with the frame rate that we used. Once again, it's just going to have some discrepancies because of that. And then our conclusion, both the models follow the same trend. So you can see that they both end up in the same stationary moment, as you can see by that nice slant right there. But there are some discrepancies in the extended system because of the frame rate of the video, and also just because the real-world example is going to take into account different forces that we're not going to be including in a computational model. So thank you so much for watching my video, and I hope you have a great day.